Okay, in this problem I've got two masses that are separated by some distance, and then there's a third smaller mass that's placed in between. I want to find the magnitude of the net gravitational force exerted by these two on the individual mass. So you could do this two ways. You could do this the long way, and you could figure out what's the force between these two, right? And then you could go figure out what's the force between these two. And then you could take those two vectors and add them up, right? So one will be pulling this way and the other will be pulling that way. So you can just take those two vectors and subtract them because they're pointing in opposite directions. You could do that, right? But the easier way would be to call this the distance, call this the midpoint, right? So from here to here, just call that R, right? And because it's the same, whatever this distance between the two is that divided by 2, right? So in my case, I'm going to use, I'm going to do GMM, the gravitation formula. But my R is going to be 0.413 divided by 2. I'm going to cut this in half to give me R, right? And so we'll call this the mass of the big one, and we'll call this the mass of the little one. So if I was going to write a formula, we'll do this an easier way, right? I'll say the force from the big one, right? I could do G times the mass of the big one times, we'll call this just M, over, this is my R, right? I have to cut this in half, over R squared. And then I'll call the force of the little one, G times the mass of the little one times the middle mass over same R squared, right? So see how a lot of this stuff is the same? This is the same, this is the same, right? I can take these two things and I can say the vector sum is subtracting them, right? So it's just this minus this, right? So if I say G mass of the big one times M over R squared minus G mass of the little one times M over R squared, right? That's going to be equal to the force acting on this mass, right? And so see how, let's see, I can pull out some of this stuff that's the same, right? So G is the same in both of them, M is the same in both of them, and R squared is the same as in both of them. And then I'm just multiplying that by the difference in the two masses. So the difference between the big mass and the little mass, right? So I can do this where G is 6.67 times 10 to the minus 11, right? I can plug that in for G, and then I know my little mass, right? That's M. I know R because I cut it in half, and I can solve that, and that's my force, right? So I mean, it's the same thing as doing it the other way. It's just skipping a step of having to solve the two individual things. I can just use this to get that. Okay, the second part says, leaving the distances fixed, at what distance does this experience a net force of 0? So now the question is, where is the force from the big one going to equal the force from the little one, right? So where is this force acting on this one going to equal this force acting on this one, right? So it's a different question. So to do this, let's make a couple definitions, right? So I'm going to call this distance D. Right, this will be D. That 0.413 in my problem, that'll be D. And then I'm going to call R the distance from the big one, right? So I don't know, again, now I'm doing this differently. So now I'm going to call the distance from the big one, I'm going to call this R. And that means that if this whole thing is D, and this is R, over here, this distance is D minus R. Okay? So distance from the big one to there is R. Distance from the little one to there is D minus R. All right, so let's write an equation that says this, right? So I'm just going to substitute in the gravitation equation for these two forces. So I can say G times mass of the big one times the mass in the middle over, this one is R because that's the big one, so over R squared equals little force. So G mass of the little one times the mass in the middle over D minus R squared, right? Oh, that parentheses should be, that square should be out here. D minus R quantity squared, right? Because it's R squared. Okay, So if I do this, right, oh, these are equal. So let's cancel stuff that's the same, right? So G is in both of them, that's a constant. M is in both of them, that's a constant, right? So really I'm just saying that mass of the big one over r squared equals the mass of the little one over d minus r squared, quantity squared, right? And so if I do a little more algebra, I'm going to cross multiply. So the mass of the big one times d minus r quantity squared equals mass of the little one times r squared, right? And let's square root both sides to get rid of the squares. So I'm going to square root both sides. So now I've got d minus r times root mass of the big one equals r times root mass of the little one. Oh, I'm done. So if I plug this in here, if I distribute that in, right, I can get d root mass of the big one minus r root mass of the big one equals r root mass of the little one, right? Okay. And so I'll combine the r's, right? So d root mass of the big one equals r root mass of the little one plus r root mass of the big one. And now I'll pull the r out, right? So I'm going to pull out the r, and then I'm going to divide that over, and I can get r, right? So I'm going to pull out r from both of these. So r is going to equal d times root mass of the big one over the sum of root mass of the little one plus root mass of the big one. There we go. Not terrible, but a fair amount of algebra, right? So to get the second one, if I plug in my masses for them, notice it doesn't even matter what this one is. The distance is what determines it, right? So if I plug in my mass of my big ones, my little ones here, and I plug in the total distance d for d, that'll give me r. That'll tell me where the net force is 0.